today. Okay. So we're going to switch gears a little bit. We're going to do a lecture on pendulums, and then you'll have some practice problems on finding the time or the period of the swinging pendulum and also the length of it. So I'll give you those formulas. What I like to do sometimes with the lecture is practice solving algebraically, just so you know if you're able to do that, especially if you plan on taking Physics B next year. I believe all of you guys will, or most of you, I think Logan's already in Chem A, but most of you will go into Chem A next semester, and I'll get a new group of Physics A. But when you take Physics B next year, which I'm assuming a lot of you guys will, because I think this is the high math rotation, third hour, I think you'll have to solve using algebra instead of what we've been doing and giving you the formulas this year. So we'll practice those. Learning targets for today is just to explain the change in forces of a simple pendulum problem, and then correctly solve them using the given formulas. And like I said, we'll practice on the PowerPoint, and then I'll have you type in the chat the correct answer before I show it, so you can check to see if you're at least typing it into your calculator the correct way. All right. So here's the lecture. Again, what I've been doing is sharing these, not just the video recorded part, but the actual video lecture without all of the talking in between. So you'll have those in your Google Classroom. And if we take a test on this again, I'll give you a study guide sheet that you'll probably be able to use. But if not, you have the lecture here also. So a little easier with the virtual stuff that we've been doing. Okay, so just follow along here. Coach Roop starts by going through the history of some stuff and then gets into the formulas and a couple of practice problems.
This is something completely different. Today's journey takes us to the Piazza de Miracoli, quite literally the place of miracles. But you all know it, of course, as the Leaning Tower of Pisa. Bet you didn't know that was part of a church. Actually, the Leaning Tower of Pisa is a part of the Cathedral of Pisa. It's a carillon. It's a bell tower. The main church, or the Duomo, and the baptistry that go with it. Interestingly enough, one of the Renaissance cathedrals, this isn't one of the big ones. The original burned down in the 11th century. They started building this one in the late 12th century, before the really big ones come along. And common to all of the Renaissance cathedrals, notice the architecture. They are all built with the same general floor plan. It's easily recognizable. They're built in the shape of a cross. Well, today we're going here to study simple harmonic motion. Now, as I said, the piazza itself isn't a big Renaissance cathedral, although you do get some scope size when you look at the 6-foot person standing here in the front and wonder how many of them does it take to get to the ceiling. Well, as you enter the church, well, yeah, it is a big barn. The Duomo, the Cathedral of Pisa, you are a long way from the back of the church to the front. Hard to even see what the point of today's lecture is all about till you get closer. Well, let's walk halfway up, and here we are halfway to the front. And what we'll be talking about is located dead center right there. Galileo found this one day bored in church. Well, he'd been to church, and remember, church back then is 2 hours long, and he had done everything you can to that point. He'd studied the architecture, the Roman arches that you find on the sides compared to the Gothic arch located at the front. The Gothic arch at the front, it's peaked rather than rounded, although the others are still rounded. This is why it can't be one of the big ones yet. It's not the use of the Gothic arches that will come later to make it the really big cathedrals. Also, you can look at the front of the church and up into the ceiling, you can see a Raphael fresco. It's called The Ascension of Mary, Mary rising bodily into heaven, borne aloft by the angels. Interesting thing about frescoes, you have to paint them small section at a time. You put a layer of wet plaster on the ceiling, and then you paint the plaster before it dries so the paint soaks in. That's why frescoes last so long. You're looking at a 600-year-old ceiling painting. Well, Galileo's point of emphasis isn't the ceiling, it's this, Galileo's lamp. See, Galileo was sitting back in the church and was kind of bored as church can get. And as he's looking around the church, he's noticing that his lamp is swinging back and forth. Then he notices the other chandeliers are swinging back and forth. And some swing faster than others. It hit him like a lightning bolt. He looks at this and he thinks, aha, the grandfather clock. Well, no, he won't come up with the grandfather clock, but he does come up with a fundamental theory that makes grandfather clocks possible. It'll be actually after his death, when all of his works are published, that a Dutch scientist, Christian Huygens, actually builds the first grandfather clock by taking Galileo's law and putting it with a couple of weights to give it a swing and a 60-tooth saw blade with a rocker arm to make the grandfather clock work. Well, Galileo doesn't come up with that. He comes up with a fundamental law of simple harmonic motion. So what are we doing today? Well, first of all, we'll diagram, describe, and explain the change of forces involved in the simple harmonic motion of a simple pendulum. Calculate the period of a simple pendulum and calculate the length of a simple pendulum. So what is simple harmonic motion? Well, simple harmonic motion is any repeating motion where the restoring force, the acceleration, is proportional to the distance away from an equilibrium position. Equilibrium position, of course, being the point where all forces are equal. So if we look at a diagram, and this is our equilibrium position, we can give this forces that are identified with it. So equilibrium, the sum of all the forces at zero. That means for every positive force, there's a negative force. So equilibrium, balanced forces. You have static equilibrium, the object is motionless. Well, that's where our pendulum will start. You have dynamic equilibrium, where everything is moving at a constant velocity.
When you look at this PowerPoint too, and he's going pretty fast, or I'm going along pretty fast because there's nothing, you don't have a sheet at home to fill in, but just know, and you know the setup of our test by now, that these are good test questions. So balanced forces being equilibrium, where you have your positive forces equaling your negative forces. And then a couple more vocab words here: static equilibrium, where the object is motionless, and dynamic equilibrium, where you have motion at a constant velocity. So again, you know the setup. Most of you guys did a really good job on the test before Christmas break, but we get those multiple choice questions right from the PowerPoint here. And if you didn't take the test yet because you weren't there that Wednesday before Christmas break, I'll probably have you do that when we get back next week, one of those days.
Dynamic equilibrium is your car in cruise control. So let's look at the equilibrium position and the simple pendulum. Well, to make a pendulum work, I have some mass held by a string rope chain. And at the equilibrium position, the forces are, first
Sorry, I shut down instead of playing playing what I was supposed to play. Hold on a minute. Let me share that again. Oh, that's what I was going to say. When you look at this diagram that I'll share again, when you look at this diagram that I'm presenting, oh, darn it. Hold on. Let me get to the right one. When you look at this on the PowerPoint, think of the net forces that we covered before the break. And those are the same forces that he'll be talking about here. So, again, when you look at this PowerPoint here, think of the net forces that we talked about before the break. Sorry about shutting that off on you or leaving. I actually left you guys.
First of all, the tension pulling up along the string and the weight pulling down towards the center of the earth. And as long as we don't push on the pendulum, those forces are equal. But I grab my pendulum and I pull it to the left. Well, now my tension is still along the string and weight is acting towards the center of the earth. Oh, but I'm at an angle. Uh-oh, angles. Oh, that's right. We now have sines and cosines involved that produce a net force back towards the equilibrium position. We let go of our pendulum and it swings back to the center. It still has the tension and the weight. These forces are now equal, but my object is moving. And Newton's first law says objects in motion remain in motion. So my object has inertia, which causes it to swing to the right-hand side, where again, the tension is along the string and the weight is towards the center. And since they're at angles, I now have a net force back towards the center. It swings back towards the center, where the tension and the weight are equal to each other. I'm at equilibrium, but I'm in motion, and objects in motion remain in motion, so I have inertia. And then I let it swing again. It goes to the left where the net force pulls it in. It goes to the center where it has inertia. It goes to the right where the net force pulls it in. It goes to the center. It goes to the left, to the center, and you have simple harmonic motion. Simple harmonic motion. You can use this simple harmonic motion to calculate time. See, the time was two ways we keep track of the time for the pendulum. First of all, there's the period, the time for one complete oscillation. There's another way we keep track of time, frequency, the number of oscillations per second. Capital T stands for period, or repeating time, time for one complete oscillation. A little curly Q scripty looking F we use for frequency. And there is a mathematical relationship between period and frequency. Period T is 1 over the frequency, and frequency is 1 over the period. Well, Galileo looked at his swinging chandelier and wondered what factors could affect the period of a pendulum. He goes home to experiment and finds out that one thing directly affects the period. And that big chandelier, you would think, well, it has to be the mass. Heavy things have to swing faster than light things. Well, no, as it turns out, the length of the period only depends upon the acceleration of gravity and the length. T is 2 pi times the square root of L over G.
Okay, so this is what I was talking about again. This is a formula for determining the time or the length of the period. or the time of the period, capital T. But you should also practice solving for L, length, and solving for gravity. In other words, getting these alone, doing the opposite of what they're already doing. You don't have to do that, but I think it's good practice for Physics B. We will actually give you the formula for length and the formula for gravity, but you can practice solving that and see if you get the same formula that we give you.
Well, what then is the period? You know me, brand new shiny equation. Let's take it out for a test spin, see what happens. Determine the period of a simple pendulum with a length of 1 meter. Read it. After I read it, here's my object. It has a length of 1 meter. Read it, diagrammed it. Now I list the length of 1 meter, the acceleration of gravity, 9.8 meters per second squared. What is the period? Well, read it, diagrammed, written, given, is no looking for. Pick my equation. T is 2 pi the square root of L over G.
Okay, so here's what I want you guys to do. Using a calculator, try to solve for the period. Try to solve for capital T. You have your givens over here. So you want to type it into the calculator the correct way. And don't put it in the chat yet. Just try to come up with the correct answer, and then I'll cue you on when to put it into the chat. But solve for T, solve for the period of this pendulum with a length L of 1. Gravity is still 9.8 meters per second squared. And again, what I like to do, some of you know how to type this whole thing into your calculator at once, but I like to do each step individually. So I'll do L divided by G equals, take the square root of that equals, and then times 2, and then times pi. For pi, you can just use 3.14. For pi, you can use 3.14. Okay, try that. I'm going to do it also, and when I get it, I'll cue you to type it into the chat. And your answer should start with a 2. Your answer should start with a 2. So another 15 seconds to try to come up with that. All right, get your chat ready. And then on the count of 3, type it into the chat. 3, 2, 1. Type your answer. Hey, good job. That's good. Tegan, Austin, Brooke, Kennedy, Anna, Cole, Whitwam. Okay, good. So you should have got 2.00 something, or 2.01, 2.006. And then let's look at it with the correct units.
Square root of L over G, or 2 pi the square root of 1 meter divided by 9.8 meters per second squared. Grab your calculators. What do you get? Correct. 2.007 seconds. Wow, that's close. Tick tock. 2.007 seconds. Oh, that means for every 1,000 swings, it's going to be off by, 0.7 seconds, or for 10,000 swings, 7 seconds. It's never going to be able to keep close to accurate time. So if it's off, I need to correct that. I got to change the length. Well, that means I need the law of pendulums and algebra. Oh no, I hate algebra. Well, the algebra is pretty straightforward. Let's take t is 2 pi the square root of L over G and solve for length. Well, how do I do that? Well, t is 2 pi the square root of L over G. I got to get 2 pi to the other side, so I divide. I have t over 2 pi is equal to the square root of L over G. How do I get rid of the square root? Correct, square each side. And I have t squared over 4 pi squared is equal to L over G. Well, G's at the bottom. I got to get that from one side to the other. How do I get it to the other? Multiply each side by G, and the length for any time I want is t squared G divided by 4 pi squared. Well, you know me. Let's take this out for a test spin, see what happens. Whenever I have a physics problem, the first thing I have to do is, what length must a pendulum be to have a period of exactly 0.5 seconds? That means tick tock, tick tock. It will make 2 swings out and back in 1 second. Oh, we're talking about a cuckoo clock. Well, I've read it. After I read it, indeed, is my pendulum and a period of 0.5 seconds out and back. Read it, diagrammed it. Now I list. Period is 0.5 seconds, and G is 9.8 meters per second squared. What's the length? Well, L is equal to t squared G over.
Okay, try this one real quick on your calculator. Use the givens. Remember for pi, 3.14. And remember to do each step, one step at a time, or if you know how to type it into your calculator all at once, do it that way. And I believe your answer will start with a 0 and have a 6 in it. Start with a 0 with a 6 in it. And it'll be a small number. Alexis, it's just do the square the pi, so 3.12 squared or 3.14 squared, and then multiply it by 4. That's just multiplying pi by 4. But do the pi squared first. Or divide by 4 and then divide by 3.14 divided by 3.14. Okay, about 10 more seconds. And listen, if you don't get the answer right away, again, it should start with a 0 and have a 6 in it. If you don't get it right away, then you can always go back and practice on your calculator. From knowing the answer and working towards it sometimes helps. Okay, type it in 3, 2, 1. Chat it. Good job, Brooke. Tegan, add one more 0 to it. Good job, Haley, Bree. Good. Good, Mason, Kennedy, Riley. Good. Okay, let's look at it.
Over 4 pi squared. Read it, diagrammed it, and gives me looking for. Pick my equation. Now I have to, and parentheses are important. 0.5 squared times 9.8 divided by, open another center parentheses, 4 times pi squared. And my answer, the length of 0.062 meters. or 6.2 centimeters. Sounds like.
As you work through these problems too, you should see a correlation in the length of whatever it's swinging on and the timer period. Okay. Short length, quicker period, long length, more time or a longer period.
Like a cuckoo clock. Well, what else can I find? Well, t is 2 pi the square root of L over g. I can use this to solve for the acceleration of gravity. I can measure the acceleration of gravity directly with a good pendulum. So how do I solve for g? Well, t is 2 pi the square root of L over g. I want to get 2 pi to the other side. Divide again. I have t over 2 pi is equal to the square root of L over g. Get rid of the square root again. That gives me t squared over 4 pi squared is equal to L over g. Well, I want to take and solve that for g. So I just divide each side by L. Oh, careful. This is going to give you t squared over 4 pi squared L is equal to 1 over g. To get rid of that 1 over g, I invert both sides. And the acceleration of gravity is 4 pi squared L over t squared. Not only here, but anywhere. This will work on any planet or moon you wish to visit. The acceleration of gravity at that point will be 4 pi squared L over t squared. 9.8 meters per second squared only works at the planet Earth at sea level. It's actually a little bit less up here in Michigan where we're 800 feet above sea level, or Denver where you're 5,280 feet above sea level, or Mount Everest where you're 27,000 feet above sea level. There we are, ladies and gentlemen. Galileo 400 years ago and the fundamental theories to build the first timekeepers, grandfather clocks, or the fundamental theory to measure a constant everywhere you wish to travel.